All right. Good morning, everyone. This research was jointly conducted by me, my advisor, Dr. Judge, who's sitting back there, Dr. Rangarajan and Dr. Ranka from the Department of Computer Science and Information Engineering in the University of Florida. I want to start by thanking NASA for supporting this research through their terrestrial hydrology program. My talk is going to be in 5 parts. In the beginning, I'm going to talk about why do we need to downscale and what is a good downscaling algorithm. Then I'm going to talk about the downscaling algorithm that we proposed and used. And then I'm going to talk about the synthetic data set that we developed to validate our algorithm. I'm going to present some results and then conclude my presentation. Soil moisture is a very important variable as it modulates the energy fluxes at the land-atmosphere interface. It is essential to have a good knowledge of soil moisture to simulate processes like evapotranspiration, runoff, and crop growth. Fortunately, soil moisture, the relaxation frequency of water is in the gigahertz range, so we can use microwave observations to retrieve soil moisture. We have 2 satellites that are dedicated for soil moisture studies. The first one is SMOS by the European Space Agency, which can retrieve soil moisture at a resolution of 36 kilometers. And the next one is the recently launched SMAP, which we are very excited about, which can retrieve soil moisture at unprecedented resolution of 9 kilometers. And we are looking forward to have more images like these available operationally. Although the 9 kilometer spatial resolution is very good for hydrometeorological studies, for agricultural studies we need even finer soil moisture. And the reason is that even within one SMAP pixel there is a lot of spatial heterogeneity, as you can see, that needs to be characterized. And for that we need downscaling. So let me present a brief context of the study. We can retrieve soil moisture from brightness temperatures at coarse resolutions. We can retrieve soil moisture from radar observations at much finer resolutions, but we also need knowledge about soil roughness and vegetation structure for this soil moisture to be accurate. What SMAP has done very successfully is combine these 2 observations and generate a merged soil moisture product, but this is currently too coarse for agricultural studies. What other downscaling studies do is use geostatistical, empirical, and physical models to convert this coarse-scale soil moisture to a fine-scale soil moisture with resolutions of less than 1 kilometer. What this does is, because downscaling is basically an ill-posed problem, it amplifies the retrieval errors that are present at this level through the ill-posed operation into the downscale soil moisture. It also doesn't consider that the soil moisture here has spatial autocorrelation, and it considers the soil moisture as independent, identically distributed quantities, which leads to errors. A better approach is to directly downscale the satellite brightness temperatures instead of downscaling the soil moisture. And there are a few studies that have done this, but they all use biophysical models, which do not work well when the coarser pixels have heterogeneity, spatial heterogeneity in them, either land cover heterogeneity or different meteorologies. So we decided to downscale brightness temperature, and then soil moisture can be retrieved if necessary. So now I want to talk about what is actually a good downscaling algorithm, right? And what we did in this study to make our downscaling algorithm good. So firstly, we need a downscaling to have low errors. So for that, we downscale TV non-linearly so that the retrieval error is not propagated. Next, we need the downscaling algorithm to be applicable to heterogeneous landscapes. If my downscaling algorithm only works for bare soil, then it is not very useful in an agricultural scenario. So what we did for that is use multiple models and develop multiple models based on other auxiliary fine-scale information so that my heterogeneity is still there in the downscale soil moisture. We also decided to use spatial information in the downscaling model so that the errors due to spatial autocorrelation issues are resolved. And finally, we wanted it to be simple to implement and use operationally. And I hope that I can bring this fact about in my description of the methodology. So what do I mean when I say multiple models? What other studies do is they use a single regression model for the whole study region. And what this does, it leads to noise errors in the downscaled product. As you can see, the downscaled product has a lot of noise compared to the true product. What we did was we divided our study area into contiguous regions, and we developed one model for each region, and this improves the downscaling result a lot. So how did we divide this? We did this by using a two-step methodology. So for the first step, we used high-resolution remote sensing products and used a multidimensional clustering algorithm on these and developed cluster labels. And in the second step, we used the cluster labels along with some fine-scale brightness temperatures as training in a regression framework to downscale soil moisture. So first I'm going to talk about my clustering algorithm. Traditional clustering algorithms work very well when the clusters are regularly shaped. So here is a very simple illustration. There are two features, and as you can see that the very popular K-means algorithm clusters based on regular shapes and cannot distinguish irregularly shaped clusters. And this leads to a lot of errors. We can use more sophisticated information theoretic methods, but even information theoretic methods work on parametric models which assume a shape a priori and then cluster based on that shape. So they, for example, Gaussian mixture models might assume a Gaussian distribution of the clusters. But we did not want to make any assumption about the shape of our clusters. So what we did was we developed a non-parametric version of information theoretic clustering and used the Cauchy-Schwarz divergence to cluster our data. So the Cauchy-Schwarz inequality for vectors is very simple. The left-hand side of this equation increases if the vectors are very different, and if the vectors are same, it's 0. We can do a vector space transformation and replace the vectors by a probability density function of the clusters. So in this case, if the probability density functions of the clusters are very different, then in this example you can see that the image is not really well clustered. So the probability density function distance is small. But then if I have a better clustering, then the distance will be large. So if I maximize the left-hand side of this equation, then I can get a good clustering result. Now, a naive way to do this is to just iterate through all possible clustering values for these pixels. So make every pixel, assign every pixel every cluster number, and just randomly find the best clustering algorithm by searching for the maximum distance. But for our case, for the number of pixels and the number of features that we had, it would take 2,500 to the power 11 iterations to do this. And we have a way to do this in just 30. So what we do for that is use the fact that this lies in a vector space and construct estimators based on information theoretic quantities, and then do a stochastic gradient descent. So from basic calculus, we'll take the derivative of this and then assume that it's a convex problem, which it is if the clusters are well separated, and find the minimum. He also added a regularization term. What this does is it allows my clusters to take fuzzy values, so each pixel can belong to 2 or more clusters if we add this term. What we also did to ensure that our clustering had the best result was change the kernel width. So this is called kernel annealing, and if I change the kernel width across iterations, then I can get to my result much faster, since the kernel width controls the fineness of my clustering algorithm and the scale at which it resolves details. So if I use this algorithm, then oddly shaped clusters are not a problem, and we can recognize any shapes in the clusters. So after we have the cluster labels, we use in situ brightness temperatures that are for training, and the in situ brightness temperatures were estimated using the tau omega model, and we consider the soil to be a non-isothermal rough surface. We consider the vegetation to be an isothermal layer with diffuse boundaries, and the downwelling sky temperature was considered to be 5 Kelvin. The regression framework we used was a kernel regression, because linear regression tries to minimize the mean errors. Nonlinear regression, while it's very powerful, has errors, spike errors between samples. So regularized kernel regression minimizes errors at each point but does not have spike samples. For that, we replaced the dot product with a kernel evaluation and estimated the soil moisture from that. The synthetic data set we used was in north central Florida, and we had dynamic lance cover of corn and cotton and bare soil. This was the features that we developed for this study. Out of these, the first two were observed, and the last three were simulated using a crop model. We selected 25% of the pixels randomly for our training. So this is the result of the clustering algorithm. As you can see, the inputs are very heterogeneous and vary a lot. And at first, the clusters are assigned randomly, but with the iterations, you can see that the clustering becomes better as the kernel width changes on the left. And as the kernel width gets lower, my clustering performance improves a lot, and finer details are being resolved. So this is the clustering performance at the end that we had, and this is from the k-means algorithm. As you can see, the k-means algorithm has many errors at the boundaries that we avoid using our algorithm. The overall downscale results are presented by land cover. For bare soil, the errors are a bit high, but this was due to vegetated pixels being misclassified at the fine scale. And once we take out the misclassified pixels, our bare soil results improve a lot. The corn results and the cotton results were less than 5K for all the times. We spatially averaged the error, and so the red is the error and the blue is the standard deviation, and found that the standard deviation, as expected, was more during the vegetated season than during the bare soil season. And the day at which the standard deviation and error was the highest was 255. And for that day, as you can see, that the errors are mostly noise that has not been disaggregated, because you cannot disaggregate 100% of the noise. And they are like per pixel levels, and if I didn't show you that, then they look almost the same. So what did we learn from this algorithm? The very high level overall things that we learned from this algorithm was that multiple models always work better than single models for downscaling. The predictive capabilities of having a nonlinear regression outweigh the additional complexity that it poses. And what we want to do after this is use active observations, so radar observations, in conjunction with brightness temperatures. And for that, we do need new features, and we are working on that. And we want this algorithm to be applicable to data sparse regions where there's no training data. So for that, we do two things. First, we utilize temporal dependencies in the data in addition to the spatial dependencies. And we also use representative regions. So we use regions similar to the data sparse regions and develop an algorithm on the similar region and then apply it to the data sparse regions. Thank you for your attention. That's all.
Questions? Yeah, thanks a lot for the presentation. I was wondering about the clustering, because you mentioned that somehow for your stochastic clustering to accelerate the process, you need the clusters to be well separated. So I was wondering what would happen if you cannot find well separated clusters. For example, if you use the k-means, the traditional k-means, and you run your model.
So what we found out that using traditional k-means was actually worse than using a single model. Because what happens if you use the k-means is that you have really large errors at the boundaries, right? Because the boundaries are all corrupted. And another technicality that I didn't really go into much was that this is actually fuzzy clustering. So my boundary pixels actually belong to two clusters. It belongs to the vegetated cluster and it belongs to the bare soil cluster. So my errors at the edges of the fields, if you notice, are very low, right? So if you use k-means, what will happen is that your results will look something like, wow, that's a lot of clicks. It'll look something like this. But then you'll have a lot more errors at the boundaries. Yeah.
Yeah, I think follow on that, when you do k-mean, you got a very bad result. But I would say it's sensitive to the number of classes you define. So how many of clusters did you use?
So that's a very good question. The number of classes that I used is cross-validated, so it changes based on the day, right? So if for this day, for example, it's all the features are like very heterogeneous. So we have 5 classes. But then for a day when there's only bare soil and the whole region there's no rain, right? So we can just have 1 class then. So this is cross-validated, and what I use for cross-validation is maximum likelihood. So I calculate the maximum likelihood of the error given the number of clusters from the data, and then that's the method I use to calculate the number of clusters. And I did that both for this method and the k-means method. So I did not discriminate.
Okay, I have a follow-up on Antonio's question. You answered the question by saying that the k-means has high error at the boundaries, what we see there, right? And then you said at your boundaries, you have 2 classifications, at those boundaries. So if it's 50% possibility, it could be one or the other. I don't understand.
Yes, that's also a very good question. This is actually the maximized version of the clustering. So if it shows blue, then it has more membership to the vegetation than to the bare soil. But you're absolutely right, and this is the reason why we have this. So let me go into a bit more detail. So this is an entropy regularization term, and this is, as you can see, the membership vectors, right? So what this term does is that it tries to decrease the entropy in the membership vectors. So you can have a situation where 1 pixel belongs to all the clusters equally, right? So that would be a very naive scenario, and we don't want that. So what this does is force a pixel to belong to at most 1 or 2 clusters, right? So if it belongs to at most 1 or 2 clusters, then we can be sure that that clustering comes from somewhere. And this, we have confirmed this with our results. And as I said, the clustering results that I show is a maximized version of the membership vectors. So for example, at the boundaries, what we had was a boundary pixel was 0.7 belonging to the vegetated region and 0.3 belonging to the bare soil region, right? And this corresponds to the fact that these are 1 kilometer pixels, and they have that fraction of vegetated and bare soil land cover at a lower spatial resolution.
Okay, thank you.